The following is a production of the University of Minnesota.
So today we have with us Stephen Sailors, and he is currently employed as Senior Specialist Electrical Engineer by Vestas Americas, a division of Vestas Wind Systems. In this capacity, he serves as internal subject matter expert on electrical power generation systems, wind turbine, design and transmission system, interconnection and integration issues. Additionally, Steve is on the adjunct faculty of Portland Community College and the Oregon Institute of Technology, and is also an instructor at the University of Wisconsin-Madison's Extension Learning Program. While working for the Bechtel Power Corporation of San Francisco and Portland General Electric, he was assigned to the design, construction, and operation of electric power plants, mostly nuclear and coal-fired, as well as power transmission and distribution projects. He's also a member of the Order of Engineering and was awarded the IEEE Millennium Medal in 2000 for services to the Oregon section. So we welcome you, Steve, and you can start with your presentation now and keep telling me when you want me to move to the next slide.
All right, then. Well, thank you for the introduction, Anita, and thank you for the invitation to present here to the University of Minnesota and to your class here. Just a quick word about Vestas Americas. We are we're a division of Vestas Wind Systems from we're a Swedish wind manufacturer, and that's basically all that we do. To specialize in wind. Some of our competitors make a lot of products for the general electrical industry and power transmission distribution industry, but we just specialize in the wind turbines themselves. And as such, we are the world's largest manufacturer of wind turbines. Okay, change slide.
And Steve, can you also be a little louder?
Okay. Change slide.
Yeah, I'm on the overview slide.
On the overview slide. Okay, well, we like to kind of present is the information on the wind turbine generator itself, which is the integral part of the wind power plant, as you see in the bottom. Go into the various aspects of what the equipment, modern wind turbine looks like, some of the protection features and control features from the wind turbine itself. We connect the wind turbines together. How many we're going to have on any given project. It could be from 1 to maybe 200 wind turbines on a particular project. And we collect them through this collection system, which we'll talk about. It's usually a combination of overhead and underground constructions, very typical of the same kind of equipment used in the regular electrical distribution type of systems that bring power right to your house. The collector system accumulates all the power that's being generated from the various wind turbines, plugs it into a central substation, and to make our interconnection with the power grid at that point. Sometimes at the distribution level, meaning at medium voltage from 1,000 volts or really from 12,000 volts to about 45,000 volts. But the tendency has been for larger plants to be connecting to the transmission system, to the high voltage transmission system, which starts at about 1,000 kilovolts up to 230 kilovolts is practical, although we are seeing some constructions now at 345 kilovolts connected into the bulk transmission system. The wind plant itself connects to the grid through the substation. We'll look at the wind plant, its basic design and control, and some of the interfaces that we do through what we call SCADA, the supervisory control and data acquisition circuit that not only records information about the complete plant operation, it also provides a great deal of controllability of the wind power plant to operate as any other conventional power plant would be required to by the transmission system operator, or what we call a TSO. Okay, next slide. The design of the wind turbine, this is kind of shown here. We've got a 20A, and you've got two major aspects to a wind turbine, the mechanical side and the electrical side. What I've highlighted here is some of the major components, both on the electrical systems and in the electromechanical systems here. And we'll go over each one of these in a lot more detail. But basically, on the mechanical side, we have the blades, the rotor make up the front part, with the part that actually captures the energy from the moving wind. Translates that energy as a rotation of torque through the drivetrain. And we'll talk about the gearbox here, because this is a major component that has a lot of issues related to it, both good and bad. But also, of course, the aspects of using gearboxes versus not using gearboxes. We have several systems of booking systems within the wind turbine. I've highlighted the hydraulic system and the lever system as two very obvious ones. As you see later in the presentation on the blades here and some of the other control aspects, the hydraulic, some manufacturers use hydraulics to pitch or turn their blades on their axes so that we can detect the energy extraction, maximum energy extraction from the wind. And other manufacturers use electric actuators to fix the blades also. So anyway, it's a design choice made by a manufacturer to use hydraulics or electric for the blade pitching systems. Another major set of motors in the wind turbine would be the yaw motors, which actually allow it to rotate on top of the tower only 360 degrees. It actually lets it rotate about 3 or 4 full rotations of the nacelle, which is what you see here, the box up on top of the tower. Because we want, in this type of design of wind turbine, that the nose cone in the front of the rotor should always be pointed into the wind. There are designs where we call downwind designs, where the rotor itself would be on the downwind side of the nacelle. But we get negative effects from tower shadow, blocking the wind before it hits the blades, and taking a good amount of energy out of the capability of the wind turbine to extract energy from the moving airstream. The modern design, what they call the Danish design, is to have distributed wind turbine with the horizontal axis and what we call an upwind type of design here. Meaning the blades are in front of the tower. The yaw motors maintain that configuration at any time when the wind is blowing and is changing and coming from different directions. And we'll try to keep that nose always into the wind. On the electrical side, of course, the heart of the beast is the generator. This is what we're trying to obviously do, is create electrical energy, converting the kinetic energy from the wind to the mechanical system, and converting it to electrical energy that to be delivered through the transmission system, and ultimately out into our load centers, which are major cities and power pits and things. The generator is a low voltage generator, meaning it's less than 1,000 volts usually. That is certainly the standard today. So we need a supplemental transformer to keep that voltage up from maybe 80 volts or 600 volts or 690 volts or even 1,000 volts to get it up to an acceptable standard medium voltage that a distribution company would generally operate at. Like it could be 13 kV or 25 kV. But since we generally bring the power out of each individual wind turbine underground, as you see in our designs here, we did a standard conventional distribution equipment like any utility would use, like I say, to bring power to your house. In your neighborhood, you'll have a small flat mount transformer in a residential community out there, and that's doing the same thing. It's taking the power and stepping it down from this medium voltage at say 25 kV or 12 kV, and then bringing it down to a useful voltage you would use in your house at 220 to 240. So to get the power from the transformer out into the collection system to the wind turbine, and we have one called down tower cables that take the full power from the generator, conditioned to the transformer, and deliver it to the collection system in these down tower cables. It goes along with the transformer, the construction of these down tower cables, because if you're not, it depends on where you're doing the transformation from low voltage to medium voltage. If you're doing it as shown in this picture, which should be component number 9 there, the red looking canisters at the back of the wind turbine, and then these are dry cast transformers that are located on top of the tower. They could be 300, 400 feet in the air. And if we make that transformation right outside the generator, then we actually save some energy losses going down the tower, and we can step up the voltage, which means obviously conversely we can step down the current. And in stepping down the current, we can reduce those I2R losses because we dropped the current significantly from 35 kV down to so something maybe in amperage from about 1,500 amps to about 40 amps. But when your losses are the square of the current times the resistance in that cable, so if you can reduce obviously the current from 1,500 amps to 30 amps, you get a significant savings in losses, the heat losses in the cable coming down to the tower. There are other configurations. You have the transformer at the bottom of the tower, which means then you've got to bring all of that current, 1,500 amps, down in multiple cables per phase, instead of using one cable that has all 3 phases in it. So it's a design choice the manufacturers make, putting the transformer in the cell or putting it down in the bottom of the tower. We'll talk a little bit more about that as we go along. The controls is really the intelligence of the modern wind turbine, and in fact, these modern wind turbines are very intelligent. They are designed to operate continuously all year long with absolutely minimal human intervention. They're made to run autonomously until their next service break, hopefully, that they have a schedule out for maintenance purposes or whatever. And in doing so, there's multiple controllers that control the full functionality of the wind turbine. You don't see it well, but the item number 6 kind of shows a black box right behind that blue generator. And in doing so, that is the main brain of the wind turbine, up in the cell. It's just a standard PLC type base control center here for the wind turbine. And all the inputs and outputs from the wind turbine, all the different systems and control decisions have to go to that top controller. And it makes the communications out to the outside world also. On the bottom controller is important because we don't normally have big personnel in the wind turbine while it's operating. You don't want people up there at 300 feet off the ground with all the kind of forces shaking that big box up there. So they can fully operate the wind turbine from the bottom of the tower where we have this bottom controller located. And it fully emulates all the functionality that the top controller uses and provides redundancy for the top controller. The hub controller, which would be item number 2, shown in the numbers around this paperweight, is actually located in the hub, and it's there to control the pitch action of the blade. You give us feedback, and then it's an intermediate controller between the top controller and the actual actuators that spin the blades on their axis. So it needs to be a hardened PLC construction because it's in this rotating hub here, and so there's always a significant force put onto the components within that controller. And to get the power, electric power to power up that controller, plus to get the hydraulic power, the actuators that would actually rotate the blades, we go through what we call a rotating union from the inside of the cell to the outside into the hub, so that we can affect the controls that the blades need to help us with, as far as the maximum energy capture and some issues for active power control that we talk about. And lastly, there's lots and lots of sensors on these wind turbines. There's around 1,200 different types of sensors. Obviously, thermal sensors, pressure sensors, strain gauges, accelerometers, flow sensors, filters, that sort of thing, that filtering detection systems that all feed into the top controller and a condition monitoring system we have installed in these modern wind turbines. Okay, next slide. Well, the rotor itself, as you can see in this snapshot, I took this snapshot in 2002 in Germany, and I was watching the field crew install one of our first modern wind turbines of this type here. I was an engineer to just have to watch the whole construction out in the field. So it gave me a great opportunity to take this picture right outside of Berlin. One of the things you see on the picture is these red paint that's on the blades. That's required by the German law in wind turbines. Different locations have different requirements for marking the blades, not only for aviation purposes, but for avian purposes, for birds and such. Now, generally in the United States, we don't require keeping the blades in this manner like they do in Germany or other markets around the world. The only place I know in the United States where we actually use blades specifically for this purpose is in Hawaii. And they require us to paint one of the 3 blades orange. So this assembly of the blades, which are obviously the long, slender units that capture the engine and the moving airstream. We're connected to the hub in the center there where you see the pick going on. And that hub is a solid speed cast steel piece. It's one of the biggest cast pieces I've ever seen in 40 years of electromechanical work. So I'm not even there's a single die cast piece here. And it's got to be strong enough that it can hold all the components together within this rotating mass. Within the hub, what you don't see there are the pitch actuators that, again, rotate the blades on their axis so that we can get the effect maximum energy capture, what we call our CP, our coefficient of power, at its optimum. And but also we use it for our control strategy, the pitching. We use it as a seat for starting and stopping of the wind turbine. And we feather in and out of the wind for several different types of active power control systems here. Over the top of that hub, which is what you see on the hub, but you don't see the actual hub interior or all the interior of the spinner there. But the spinner is the plastic piece. It goes over the hub and commonly referred to by people outside of the trade as the nose cone of the wind turbine there. You put all these pieces, the blade, the hub, the actuator, the spinner, the hub controller, it all goes into the rotor. As you can see here, it's we need two large cranes, one very large crane to do the pick, and one stabilizing crane there to be sure that even in a light wind, we don't get much sway out of it when we're actually pulling that rotor up and connecting it to. It's actually flange mounted, a large flange on the gearbox up in the nacelle. So when we assemble a wind turbine, we create the foundation, mount the tower on top of the foundation, mount the nacelle, the box with everything is in, on top of the tower, and then finally we hang this rotor assembly, which is all put up on the ground. We pick the whole rotor up and then put it onto the nacelle, like we do to the blow shaft as such. So we do, this is a typical way to do it either onshore or when we're on land. If we have a offshore installation, what we generally will do is with 2 to 3 blades on in the port, ship out the rotors, and then put that third blade on there. That way we can put several rotors on the large, and we can put the rotors up and then hang that last rotor, the last blade on the rotor when it's in the air.
Say, Steve, this is Ned. Can you hear me?
I can hear you, yes.
Yeah, okay. We only have up to 6 o'clock here, and so right now it's like 4:40. So I would urge you to speed up a little bit. Looks like you have a lot of slides here.
Okay.
And another thing is that do you have access to a landline there, or you only have a speaker phone?
What was the last part about the landline?
Do you have a landline, or you're calling from a speaker phone, right?
Yes.
But you don't have any other phone line like land connection, wired?
I do have a LAN connection. Like I can call in on that if you'd like.
What do you say?
Yeah, we could try that out if that's better.
You want me to call in on the landline? Is it?
Yeah.
Okay, let me try that here.
Sorry about you guys.
I'm calling the same number.
Yep, that's fine. Sorry about that. This is the only video conference lecture that we have. All the other speakers are physically going to be here to present, so this should not happen again. Hello?
Hello?
Oh, wow. This is way better.
Okay, that's I proposed this earlier, but
Yep, you can continue, Steve. This is much louder.
this is better?
Yep.
Okay. I'll speed up here. Okay, so next slide on blades. So the modern wind turbine, utility scale wind turbine uses there's GRPE, we call glass reinforced polyester, the type of blades here, particularly on the shell of the blade. The blade has the two major components. The interior of this spar or cord is generally fiberglass epoxyized into a very stiff construction that makes up the rigid part of the blade. And over the top of that, then we autoclave the upper and lower shells around there to give it the airfoil shape that you see. So these airfoil shapes are standard airfoil shapes used from the aircraft industry. And along the length of the blade, we use varying shapes here as we go from the root end, which is the tip, the end that connects to the road, to the hub itself, out to the very tip. The tips are very narrow because this is where most of the energy capture is actually done in the second half of the blade. And in fact, because there's almost no energy captured in the first quarter of the blade, we just have a rounded shape, as you see there, for structural, to give it as much strength as possible where the forces are concentrated at the root. We put because the wind doesn't put an even loading onto the blade, it gives it a different angle of loading on the blade. We have to put a twist into the blade about 15 to 18 degrees from the root to the tip. And so we kind of pre-manufacture that skew into it as we design the blade. That way all the rotor, the lift vectors along the blade line up and uniformly add up to a nice, even, straight line lift vector for the blade. Okay, next slide. We'll go on to the shaft and then the gearbox. Now, there's two types of philosophies. Either you go with a gearbox or you don't. With these kind of forces, there's dramatic wear and tear on the gear faces. And so gearbox maintenance is one of the major issues within the wind industry here. But fundamentally, we're transforming mechanical torque that is picked up from extracting the energy from the wind, translating it at low speed, very high torque, and through the gearbox, we step up the gear ratio. As you can see, a megawatt class or utility scale wind turbine, the gear ratios are anywhere from 50 and for a 2 or 3 megawatt machine, they're generally closer to 100 to 1 as far as the gear ratios within the box, which is made basically of a helical and a combination of helical and planetary gears, depending on the type of arrangement that they want to use. But the main point is to take the low-speed high torque, convert it to high-speed low torque. So we're operating about 15 RPM to 25 RPM or so at the actual rotor of the wind turbine, and we're taking that up to 1,200 or 1,800 RPM in a 6 or 4 pole generator, respectively. You can see the second bullet. Clipper uses a kind of a different arrangement. It uses 2-stage helical load splitting gear arrangement to drive 4 generators at once. And they feel the advantage of this is that if they have one generator go down, they could actually take it out for maintenance and operate it with 3 generators or even 2. So if these were 750 kW generators in this Clipper machine, you took one out, you could, so instead of having 3 megawatts, you'd have 2.25, and you could operate that way until you replace that other generator. It's just a design decision that you take from the beginning, but this is the tactic Clipper chose to use. And the last bullet there's D-Wind is a German company, and they actually use a fluid clutch, essentially, a hydrodynamic torque converter. That way they can use a synchronous generator with a fixed synchronous speed of its excitation as such, and in doing so, it changes the split characteristic. Instead of doing it electrically, like most of the other manufacturers do, and certainly this is how Vestas does it, we use electric slip. They control hydraulic slip to match up the synchronous speed of the generator with the bearing speed that you're getting from the actual rotor itself of the wind turbine. Next slide. But there are gearless designs. Enercon, Repower, other manufacturers actually try to produce a gearless design. And it's a fundamental design decision you make of how you're going to start building a wind turbine. But if you went with gearless, you obviously save the wear and tear and the maintenance point of the gearbox. But as you see, we introduced these large, have to be multi-pole now because you're not stepping up speed. And so that one of the reasons we step up the speed to 12 or 1800 RPM is we can put more power in a smaller footprint, in a smaller generator. But these generators for a gearless design have to have the same number of poles because that generator is going to operate at the same speed as the rotor is rotating for the wind turbine. And so the second pole is that the mass of the rotor generally has to be proportional to the amount of torque. And so you get these very large rotors in this type of design, but they're very heavy. And they become very costly. There's a lot of iron, magnetic ion, steel in these types of designs. And what you're seeing there is the stator. So you're very small annulus. I mean, it's very wide annulus, but very small width to that generator. So they give a compact design to the wind turbine, and again, it's a decision each manufacturer takes on when he decides how am I going to build a wind turbine to extract the energy out of the wind and convert it to electricity. Next slide. Well, we can talk about different types of generators that are commonly used in wind turbines. 15 years ago, most of the wind turbines in the world were constant speed wind turbines using the simple induction generator. SIG stands for simple induction generator, which means it uses a squirrel cage rotor design with fixed rotor bars in contrast to wound coils of conductor material in the rotor. But in doing this, because these machines have pitch blades that do not pitch, so we're counting on the aerodynamic law of stall, actually not overload this machine. The wind kept coming stronger and stronger. There's a point when the aerodynamics of the blade start to become producing turbulence on the backside of the blade, and hence you start increasing stall as the wind gets stronger and stronger. So that was the way to control overpowering a wind turbine up to about 15 years ago. And so many turbines that went in the 80s, particularly in California and early in Texas, used this type of design. More modern wind turbines for the last 10 years to 15 years have relied more on what we call variable speed generators, which we'll talk about right after this. But we have a way of identifying the different major construction types of wind turbines. And so this constant speed wind turbine is commonly referred to as a Type 1 in the vernacular of the industry now. Again, they have a fixed blade, or we can do a small pitch on the blade for a system that's called active stall. And if you've got fixed blades, when you get it at its rated wind speed and the wind keeps increasing, like I say, the stall starts to build on the blade, but it tends to overdrive the machine. You get a little overshoot of power out of the machine. And so reduce that overshoot so that we don't have to make such a robust machine to accommodate that overshoot, then we can put a slight negative pitch in the blade, have it pitch backwards, and this is called active stall, and we can eliminate that overshoot and just come to very flat rated conditions when we reach our rated wind speed. Because it does use a simple induction generator, which will have a power factor of 0.87 or 0.90 or such inductively, which means it's drawing bars from the grid into the machine, and in doing so, it will tend to drop the voltage on the grid as it's pulling those bars off from the grid. what we do is we have a set of capacitors in the wind turbine that will offset the inductive nature of the generator itself with capacitive current. And of course, the vector nature of induction and capacitance is that they are diametrically opposed to each other, and so they will tend to cancel each other. And if we get it just about right, we can have the capacitor bank give us a power factor as seen by the grid of unity, or 1. We're not pulling bars from the grid, and we're not supplying bars to the grid. And so in that way, it's a we're not doing it in an uncontrolled manner. We're going to see right after this, we want to contribute inductive bars or capacitive bars and draw inductive bars from the grid for voltage control purposes if we do it in a controlled manner. But with these type 1 machines, we really can't do that, and the best we can do is just offset the inductive nature of the generator with a capacitor bank. And these banks are multi-switched because as a certain requirement to magnetize the core of the generator, but as you keep increasing the power output, it tends to draw more and more bars into the generator. And as such, then we step in increasing amounts of capacitance to offset that as power goes up and down out of the generator. Okay, next slide. So we call this a semi-variable. It's not a constant speed like the Type 1, but it's not a true variable speed machine like what you'll see the Type 3s and Type 4s are, or even the Type 5 like I was alluding to from D-Wind. But the semi-variable was a reasonable alternative around 1995 to about 2005. Not a lot of manufacturers use this. Certainly Vestas did. Gamesa had used this, and there were some Indian companies that used the same kind of technology. But what it did is took a simple induction generator and used wound rotor inductors, brought the leads from the rotors out, and then connected them to power electronics to a 9GBT transistor that switched in a bank of resistors you'll see up on the upper left there. If we can control the duty rate switching in about 1.5 kilohertz on a 60 hertz system, we can effectively give a linear and continuous value of rotor current and thus control a little bit the rotor current as such. And in doing so with blade pitch, now we can pitch the blades, get the optimum extraction of the energy from the moving wind, and as those dynamics are happening with the wind, we can kind of follow it with this idea of variable split within the generator itself. So we've gone from a fixed slip of 1 or 2% on the Type 1 to a varying slip of up from 1 to 10%. And in that manner, it also gives us the capability that when we actually overdrive the generator, we get too much wind, we can control the power output to exactly its rated value, and we can use that extra energy. We capture it within the magnetic field of the air gap within the generator. And then when the wind dies down a little bit, that energy will naturally flow out to the grid. So it's a way to capture energy that we would have lost on the Type 1. And again, because it is it's an induction generator, it's just a wound rotor induction generator, instead of using rotor bars like a squirrel cage design, then we need to also have a capacitor bank on there that will bring us back to a power factor around 1, that we're benign to the utility that we're connecting to. We're not overexciting and causing high or low voltages on their system, just as power goes in and out and the inductive draw on the generator changes. We just offset whatever induction requirement of the generators with the capacitor bank, and we're pretty good with that. And that was fine for how wind turbine projects were run until about 10 years ago. But because of the success of wind, we've had to come up with new control strategies. As wind turbines got larger and the projects got larger, and there's more projects going in onto the grid system, then we are having a much larger impact today than we did 10, 15 years ago on the overall power delivery that the grid provides to all its loads. So we've had to change our control schemes, evolving from the Type 1 to the Type 2. And now, next slide. We've evolved to the Type 3, which is the state-of-the-art as of today. This is commonly used design. It uses a double-fed asynchronous generator. It's often called a DFAG, a double-fed induction generator. But in all reality, it doesn't work off of Faraday's laws of induction. We actually have a rotor excitation control, not just like in the Type 2 where we kind of just increase, decrease the rotor current. But here we can actually control it, its magnitude and its phase relationship between the current and the voltage. And as such, we have vector control of the rotor current. So we use this double-fed asynchronous generator, and what does it do? It increases the slip capability up to about 50%. So Type 1, we had no slip, so any change in the wind speed is automatically seen by the generator, not was so automatically seen by the power output. But with this slip control, we can actually soften the impact, and even though there's wind changes, we can store that excess energy when the wind drives too hard, like I said before, and release that energy into the grid when the wind dies down. And it's a very nice system for providing very flat and very predictable power output from the generator. Of course, we needed to have controllable pitched blades. For this, the variable speed curve comes from the blades can be changed, so we can change the speed of the actual mechanical rotor of the wind turbine. But we follow that with this slip control to give a very seamless output of power, like I say, to the grid. You'll see in the diagram there the AC-DC converters, and between the generator itself and the grid we're showing as a three-winding transformer. So we tap a little bit of the output power from the stator and feed that back to the rotor circuit, and then we control that current we're tapping back to the rotor through the power electronics to control, again, the current magnitude and phase. We can independently control the direct and the quadrature axes. So the direct axis is most notably controls active power, or P, and the quadrature axis most notably controls Q, and so affects reactive power. And reactive power most effectively affects voltage. So if we can control D, we can control active power, which basically controls frequency. If we can control Q, we can control voltage because we can control reactive power. And we do this through this part transformation, and I'll leave it to the interested student to see the derivation of the part transformation. But it's a way where we can completely independently separate active and reactive power from the generator, control them to the aspects we want to for the best power quality and best power delivery to the grid. So the rotor's reactive power capability is defined when you design the generator itself. It's got limitations to it as such, but the power factor range really depends on this motor's active power and reactive power capability curve. Those of you that have taken electrical machinery and have seen synchronous generators. This is known as the D curve on those type of machines. But the curve looks entirely differently for these type of wind turbines. Next slide. This is the newest design of wind turbines that is within the last 2 years really making its mark. Vestas has a product like this, or several products like this. All of our major competitors are promoting their new products such as this, which we call the Type 4 wind turbine, or a full-scale converter. So what we've done is taken those power electronics you saw on the rotor circuit, and we put them on the output of the stator. So instead of conditioning the excitation of the generator, we're actually just controlling the full output of the generator from the stator as it gets delivered to the grid. And we use standard IGBT voltage source converters to do this. So, but the reason we do this, now you can see we can control slip all the way to 100%. We can have total control of the slip characteristics of the mechanical energy coming in to the torque, driving the generator, but we can completely divorce that from the electrical output of the generator to the grid. And in doing so, it gives us tremendous flexibility with this type of design. And now if you see the generator design, we can use an induction generator or a synchronous generator or a variation of a synchronous generator, a permanent magnet generator, because we're not controlling the excitation anymore, or we might want to control the excitation, but we don't necessarily have to, because we can totally control the output of the generator through these power electronics and then out to the grid. Again, this may or may not have a gearbox. That's a different decision. That's a totally mechanical decision. But these converters are used as normal power flow would be coming out of the generator. We would use the converter that was got the IGBT sign there, basically for the on the generator side as a rectifier. So we rectify that, provide that onto the DC link where you see the capacitor in the middle, and then we re-invert to AC at exactly the frequency and exactly the voltage we want to deliver to the collection grid, or to the collection grid, which connects to the outside grid. So the power factor is completely independent of any generation characteristics. So voltage control is totally affected by the what we call the grid side converter as such. There's a bit of debate of whether this design gives us highly flexible functionality, control functionality over the DFAG. If you go back a slide, the advantage of the DFAG having the power electronics on the rotor circuit is we can drastically reduce the size and get pretty close to the same control functionality. Not exactly, and not quite as far, but we can get very good control functionality on this Type 3 by having the electronics on the rotor circuit, and those electronics only have to be rated for 1/3 the size of the power output of the generator. So if this is a 3 megawatt generator, we only need a converter system that will handle 1 MVA of power through it. If we went to the Type 4, go back to the Type 4 slide, then we have to have those power electronics rated for the full 3 MVA coming from the generator. So the advantage of the DFAG is that it's less costly, the power electronics are less costly, and we have a much less losses to account for, because the inverters are all about 3% efficient, but when you go 3% larger, then you obviously have got more losses with this Type 4 just in the power electronics. So this design costs more, but some of that cost we get back if we use a permanent magnet generator, I should say, is so long as the permanent magnet materials market, the global market doesn't go crazy, which it has done in the last year, unfortunately. And so there's a bit of where everyone's excited about the Type 4 generator, seeing the advantages still of the Type 3, and then it helps to keep costs down and keep the risk of costs rising uncontrollably in short term here. So there's advantages and disadvantages for all these. That's why they're all different design choices you make when you do the wind turbine design. Moving on to the transformer. First of all, can I ask, is this a good pace for everyone?
Yep.
For the presentation?
Yeah, everyone's...
We moving along fast enough? Or too fast?
Yeah, I think this is a good pace. And just a reminder, we have another 55 minutes to go.
I didn't hear any of that. I'm sorry.
This is a good pace for everyone. And I just wanted to remind you, we have another 50 to 55 minutes to go.
Okay. Okay, so now looking at the transformers. Like I said here, we showed two pictures here. One of the dry cast transformer on the right, and then an oil bath transformer on the left. And again, this is a design choice that we as manufacturers use. And the use of the dry cast transformers, again, means that you can get away with very small cables coming out of the nacelle down the tower, and you can use very flexible cable arrangements because all three phases and the grounding conductor can all fit into one cable. If we do a pad mount transformer at the bottom of the tower, as shown on the left, then we've got to bring that full, say, 1,500 amps down, and with multiple cables. And so then you've got the arrangements you got to make for suspending such cables. They're over several hundred feet. That's a lot of weight. So, and you've got to keep the cables separated for proper clearance and all that sort of thing. And so your suspending and your cable handling arrangements are much more difficult if you use the pad mount transformer. But you can easily change the size of the pad mount as you like, or put you can buy conventional distribution transformers instead of using the dry cast transformers that we as manufacturers would probably supply that are already in the nacelle when you get them on the site. So the generator, like I said, operates usually as below 1,000 volts or below. This is done so that we can use conventional workers or conventional electricians, which means not electricians who are medium voltage licensed, which is a special license and takes a high degree of training to get so that pool of electricians isn't that large at the medium voltage sizes for the kind of scale that wind has in building all these plants all at the same time. So if we keep a generator and all the components in the nacelle pretty much below 1,000 volts, we can use conventional licensed electricians, and they can be our wiremen for when we're doing the installation and commissioning of this equipment. But we've got to step up to the collection system voltage, which I show here. It could be anywhere from 10 to 35 kV. And again, generally the highest we run is 34.5 kV. We call it 35 kV, but it's actually 34.5. And that's because coming out of the wind turbine, we use underground constructions, and the standard off-the-shelf components for manufacturers for normal distribution systems only go up to 34.5 kV. And so that we don't have unique industries and components built for the wind industry, and in a pinch we can just go down to our electrical distributor and get the components we need, then we try to keep it within the standard voltages that distribution uses for routing power out to your house or within your city.
Again, I talked a little bit about the pad mount versus the dry cast, and where you mount them on the, as you can see, on the bottom of the tower versus the top of the tower. But you need to connect up to that transformer. And what you see in the picture on the left, on with that the oil bath transformer on the outside of the tower, there's got to be some way to get those power cables, down tower cables, into the wiring cabinet of the transformer. And so either they've got to go through the foundation, to the concrete of the foundation, and stub up into that transformer cabinet, or we build a penetration in the tower, as you see in this picture, and build a little wireway in the field to accommodate those cables going into the wiring connection side of the transformer box there, which, as you see, is on the right of the transformer in that picture. The last major item about transformers to consider is, well, there's kind of two things. One thing is that you don't necessarily have to have an extra 25% oversize of the transformer with the wind turbine. You can size it to 100% of the active, well, of the apparent power output of the wind turbine itself. The reason is because as wind picks up and generates more power, creates more current, which would heat up this transformer, and also tends to help cool the transformer because its rating is kind of based on the cooling designs, whether it's natural cooling, or you've got forced air cooling, or you've got oil cooling. In a small distribution transformer, you generally don't have forced air and pumped oil cooling, so you're relying on the natural ambient air moving over cooling coils to cool off the tank with the oil in it in the transformer. So when the wind picks up and provides more power, which would heat up the transformer, it also tends to provide more cooling for the transformer. And so we can get, if this was a 2 megawatt wind turbine, we could probably specify exactly 2 megawatt transformer. Some engineers like to over-design it and put some extra margin into it, so maybe they might want a 2.10 or 2.15 MVA transformer for a 2 megawatt wind turbine, but they really don't need to. When you actually do the wind, if you don't do the engineering design, then you really can't get away with it. But it's a simple calculation to include in your wind park design to say I accommodated for the cooling and extra cooling effect, and hence I can get away with a slightly smaller transformer. Next slide. The tower and foundation, this is for the civil engineers who are in the audience. This is probably the most interesting here. As you can see, we've got pictures of erecting the tower. They're generally rolled steel. We get them in big plates. We roll them into arcs and then weld them together into tower sections. The detailed drawing on the right shows 4 tower sections on that particular design of tower. And you can see how they pick the sections up, and they just flange mount them one on top of another. They're generally, like say, rolled steel, but different companies are looking at different alternatives, like concrete towers or other types of towers, composite towers and things like that. But the convention right now is still for rolled steel towers. You can see some of the details of the tower construction. There's platforms put in there. When you go 300 or 400 feet in the air, you're going to want some resting areas for the technicians as they climb up and down the towers and things, and also to stage some work within the towers. So there's multiple platforms in there, and this is what some of the section details you see there are showing. You see a stairs detail. One other aspect about this is that the tower itself is used as the main grounding conductor for our grounding system within the wind turbine. Next slide. So if we look at the foundations, I'm going to show you 2 major types of foundations, particularly used in the United States, the Spreadfoot Foundation and what they call the P&H, or the Patrick and Henderson Foundation, which they accomplish the same thing, but they do it in a very different manner. So the Spreadfoot, or inertial concrete base foundation here, uses this large reinforced mass, has a large inertia to overcome the tipping moment and the bending movement that the tower is going to present to the foundation. These are the things you need to consider here: the overturning moment of the tower with that foundation, the base shear, the vertical loading from all the equipment on the tower down onto the foundation, and then the torsional forces that, because you can get an appreciable twist, although the nacelle is yawing to keep its place in the wind, it yaws at a definite motor speed of those yaw motors. And so there is a good torsion put onto that tower as such, and was to be translated into the foundation. So the foundation is there just to hold the tower up. The tower is there to hold that box up in the air with its components to get us as high as we can in the air, because this gives us our cleanest, least turbulent air, the higher we can get up. Next slide. This corrugated metal pipe is a different design. This is, like I said, the P&H design, named after two guys in Bakersfield who basically came up with this. So it's a much cheaper design, and it accomplishes the same functionality. The tower components are flange mounted onto these foundations, no matter what they are. But whereas with the Spreadfoot, they're generally about 7 feet deep into the ground. This one's 30 feet into the ground here. It doesn't use a large footing, and so it needs to have a better contact with the ground, deep into the ground as such, to make sure all those forces are accommodated. So it uses two tubes, essentially, this inner and outer wall, and then we put rebar in between the walls and pour concrete in between the walls, and this gives us a very solid foundation. And those rebar, we can tip with the threaded connections there, so we can make that flange mount to the tower itself. Okay, next slide. The grounding systems within a wind turbine are extremely important, because lightning is one of the major damage vehicles here, or damage methods that really can bring down a turbine. So it's got this integrated lightning protection, surge protection, and grounding system all built in to the standards for lightning and for grounding. So we actually put lightning receptors into the blades to attract the lightning to these receptors, so that they don't hit odd places on the blade and crack our fiberglass shell on the blades, which would cause turbulence on the blade itself and reduce power output. So those receptors in the blades have got conductors that bring any energy from a lightning strike through the blade roots and the blade bearings that allow the blade to rotate, bring it through the hub itself, and then bring it into this integrated system we have with the wind turbine. And again, we use the tower as our primary grounding conductor from the ground point within the nacelle to where we actually inject the currents into the ground if we have a fault or a lightning strike. The system on the right around the foundation is kind of an older type of design, where we use a ring type of electrode with driven rods. You can see it's a kind of a ring that's around the circumference of the foundation, the hatched area there. And it's a full ring to accommodate 360 degrees around the wind turbine. And then we usually use driven rods then to get down and inject those currents into the earth, so that they can be wicked away naturally. And people are safe and the equipment is safe from over voltages from faults and lightning strikes. The design on the left actually has a newer design here that started around 2007, where we used the rebar within the foundation itself to form an UFER ground, a UFER, UFER ground, named after a guy in UFER during World War II who built ground systems for buildings out in the desert when the military was building a lot of construction in the desert during World War II with no water table to access. And so he used the steel within the foundation. And so we do that also. We run a copper conductor within the foundation before we pour the concrete and set the concrete. So with this copper, we connect it with the proper listed, UL-listed grounding connectors to that rebar, and that creates the foundation as an electrode. Now, this is good for grounding faults, for 60-cycle faults, but high-energy faults and high-frequency faults from lightning tend to want a less impedance of a path for its surge impedance. So the high-frequency component of the lightning strike. And so what you'll see is there's two conductors that come out of the foundation or out of the wind turbine and go horizontally in the soil about 3 feet deep for about 40 meters on either side of the wind turbine. And that is more of the lightning protection side of this integrated lightning and earthing system, where the foundation is more of the grounding or the 60-cycle fault protection for the grounding system. Next slide. We get into operation of these wind turbines as such. So we've got many control objectives we're trying to perform with the wind turbine. First off, and primary, is maximum energy capture. So one of the reasons we pitch the blades, we turn them is so that we can get an optimum angle of attack of the blades into the wind and get the maximum lift coefficient from the wind on the blade itself. We also want to pitch those blades to feather the loading, the mechanical loading that is going to be translated from the rotor as a thrust force onto the tower. So if we can pitch in a controlled manner, we can actually reduce some of the stresses the tower would have to see, trying to keep all its equipment in the air when the wind is blowing hard. So we use the control system for the load control. We call load means mechanical loading of the complete wind turbine. We also want to keep power quality as high as possible, the electrical power. We want to keep voltage flicker or voltage fluctuations from the wind turbine into the grid at a minimum. We want to keep harmonics as low as possible. We want to keep some control strategies for active and reactive power. And that leads into the final bullet there, the overall power plant performance. The wind turbine by itself performs, but what the grid operator, what the power off-taker is concerned about is the overall power coming from the whole project, with all the wind turbines acting together in concert. So we want to use controls here to ultimately, at the wind turbine level and at the park level, which we'll see here in a minute, will actually give us the best overall power plant performance and help us meet the interconnection requirements of the power off-taker, whether that's a utility district or it's a general city utility or it's a transmission company or it's a complete regional transmission provider. They all have the requirements of how the power is supposed to be delivered and how reliable it is. So this overall power plant performance is written in what they call the grid code for that particular area. And that grid code should reflect the nuances of how the grid actually looks in that particular region or in that particular area. You can't do a one-size-fits-all because if you were next to a nuclear plant, you'd have a very, very strong electrical system. And it could take a certain amount of fluctuation that if you were, say, 200 miles away from any other generating resource that could help to strengthen your immediate electrical system, and hence your system is very weak that you're pumping your power into, then small fluctuations in your power and voltage and frequency would cause large fluctuations in that portion of the grid. So the grid is not all homogeneous from coast to coast. It is strong in some areas and weak in other areas. It just tends to be where we put wind turbines these days are in areas that are very weak because generally nobody lives out there. There's no need to have a strong grid in that area. You want a good strong grid around your load centers, your cities. So where it's windy, we don't put large cities generally, and so the overall power plant performance is very important and very highly discussed these days within the wind and solar, as a matter of fact. Within the wind turbines, we've got these multifunction processors, or this PLC-based system I talked about a little earlier with our controllers. They control all of the functionality of the turbine for this autonomous operation, and also so that we can, from the outside world, find out what the turbine is doing. All the different aspects of the turbine, which components are working properly, which is not, alarms, data recording, all sorts of information that we want to understand about how the turbine is operating is all done through that top controller here, which is, again, this programmable logic controller you see in the bullet, although it could be a CAN type of system like you have in your car these days, a control area network, where they'll feed into the central top controller as such. We want to perform a certain amount of set point control for different types of processes within the wind turbine. And again, programmable logic control is very agreeable for set point control. And we've got some other software strategies that we try to maintain. And a couple of those are the power performance curve of the wind turbine. You've got to know at any given wind what is the output in megawatts of the wind turbine. It's because this guarantees what the kind of revenue that can be calculated from that wind turbine operating in that kind of wind is going to be in that particular area. So we need to fully understand that and control that. So we might have 3 or 4 different power modes that the wind turbine could operate at, but the most advantageous for the owner of the wind turbine is to have it where it captures the maximum amount of energy because that's what it gets paid for, so many cents per kilowatt hour. We also have noise control strategies that the software will affect. Sometimes the noise abatement, noise control, or sound power control more accurately, is desired if you've got people in habitable buildings within a maybe half-mile radius. So there's different needs to control the output power and the overall operation of the wind turbine based on these strategies. Next slide. So the first bit of control is optimizing the tip speed ratio. The coefficient of performance, that CP I've been talking about, the maximum energy extraction from the wind, is based on these 2 components, the tip speed ratio and the pitch angle of the blade. But this pitch speed angle, the fewer blades gives you a higher tip speed ratio, a higher lambda, and in doing so gives you the opportunity for the optimum energy capture, in contrast to the necessity for managing these electrical and mechanical loads on the tower and on the output power as such. A couple things about the fixed speed or the constant speed versus the variable speed designs. Again, a type 1 is is a fixed speed design or a constant speed design, and it achieves its aerodynamic efficiency at 1 set speed. And when the wind changes, it becomes less efficient, but we have no way to control that. The type 2 and 3 and 4 will actually pitch its blades as such, so we can control that. So the variable speed type generators or wind turbines achieve a greater efficiency over a wider range of speeds here because we can actually coordinate the whole operation of the wind turbine as the wind changes. Next slide. So again, pitching the blades allows us to slow down or speed up the rotor, depending on how we want to control, maybe for power control, maybe for sound control, like we say. But ideally, it's to optimize the energy capture by optimizing our lambda, the tip speed ratio. Like I say, also a control strategy for the power curve, as I said earlier, but also we want to flatten out the power when we reach rated conditions so we don't get that overshoot like we would with the Type 1, with overshoot of power with the Type 1. And if we can control the loading of the forces on the drivetrain by pitching in and out as such, we can, and then the tower thrust forces and such, we can get by with lighter gearboxes and thinner wall towers. And all this is cost. The more steel we have to put in to reinforce this for the higher loading forces for, say, a Type 1 versus a Type 3, is all cost. And so we can extract some of that cost just by these type of controls here on the mechanical side and the electrical side as such. And pitching blades is a big part of that. And as I referred to, we've got noise emission control strategies here that pitching the blades is the control methodology. The next slide. Pitching the blades also allows for this controlled starting, pausing, and emergency stopping in a wind turbine. We have a hydraulic brake, disc brake essentially, on the main drive shaft, but we don't. If we use that to stop the machine all the time, we'd wear out those pads very, very, very quickly. So, but we can effectively stop the machine just by pitching out from a zero angle during normal operation. Hits the blades 90 degrees to the apparent wind, and the turbine will stop within 2 or 3 revolutions. It's really a remarkable thing to see. It just power down and stop. We actually use it for starting the machine. We use a little bit of aggressive pitch to actually get the machine started in low wind, and then we move it to about a 0 datum angle on the pitch when we're in normal power operation, and then when we reach rated conditions, we're spilling a little wind so we don't overdrive the design of the machine. This newer strategy identified here, most wind turbines, when they do pitch, will pitch all 3 blades at the same common angle. So you'll have a command signal come in and tell all 3 blades to change 2 degrees, say. You could actually have a control strategy on the blades where with independent pitch of the 3 blades, and there's some obvious advantages to this. As I bulleted here, you can actually get lower thickness of the wall towers yet than just pitching it, in contrast to constant speed or no pitching at all. So as we generally use this on our largest machines to better the thrust forces and get it as small and light a tower as we can possibly get. When we're transporting towers, there's restrictions on length and width of the actual steel in the tower, but also on weight because we're transporting these over highways and rail and such. So if we can get lighter towers, it's always much more beneficial and economical for everybody. But to do this, the systems, the control system within the turbine has to have a lot more inputs and outputs, a lot more I/O for strain gauges and accelerometers that we actually put in the blade to tell how the blade is reacting to this independent pitch. If you can imagine why we do this is a blade at 12 o'clock, meaning the other 2 blades would be at 4 o'clock and 8 o'clock, then the one at 12 o'clock would have the highest forces because it's sticking up highest into the wind. So that one's going to be that one blade will be loaded more than the other two. Now think of it conversely with the one blade at 6 o'clock and the other is at 2 and 10. Now that blade at 6 o'clock is passing the tower and unloading at that point. So you're getting an uneven distribution of the thrust forces along the swept area of the rotor if you've got all three blades pitching to the same angle all the time. We can actually put in control algorithms that will learn and sense these patterns through fuzzy logic and such that we can reduce the total thrust forces on the tower from the swept area of the rotor very significantly. And so this is one of the newest control strategies within this blade pitching. Next slide. So the controls we have also, we put a lot of power electronics into these modern wind turbines. I'll just go through the bullets quickly, but we use them for soft starting. So we put silicon-controlled rectifiers on these Type 1 and Type 2 wind turbines that have very little control to them. And because, since they're in simple induction machines, they'll pull a large bar draw when the core magnetizes. And if we can slowly pull that current into the generator to magnetize the core, then we can reduce the inrush current from anywhere from 8 to 10 times to maybe only 4 to 6 times. And this is a great benefit because every time we're drawing that current off of the grid to magnetize the core of every one of these wind turbines, then it will tend to change the voltage quite a lot until the core gets fully magnetized. And so it's a way to keep our power quality and be a good player on the grid. But as I said earlier with the Type 2, these wound rotor induction generators using the external resistors to control these resistors, we've got the IGBTs and diodes to control the magnitude of the rotor current and thus the rotor magnetic field strength, and that way we can, again, control slip. On the Type 3 turbine, the DFAG, we use IGBT transformers, the insulated gated bipolar transistor here for our vector source converters for the rotor control, and we can either affect scalar or vector control by whether we're using a 2-quadrant or 4-quadrant type of arrangement on those converters. But we can control the rotor current to a very exacting level at that point, and again through Park's transformation we can effectively provide P and Q control independently, and we can completely control the power factor within the range of the design of the generator, much like a conventional generator. So with active and reactive power control, fundamentally, if we control the speed of the operation of by pitching, then we control active power. If we control active power, we can actually affect frequency regulation and frequency support. By controlling the rotor converter and controlling reactive power from the generator itself, we can actually affect voltage regulation and voltage support. Just a quick thing about the time constants is just if you look at them, you see from top to bottom they're getting faster and faster. The wind changes here in about 15 to 20 millisecond range. The pitch controls are much slower than that. But we generally work both controls together, the pitch control and the rotor current controls together to give us our power profile that we're presenting from the wind turbine. And as you can see, 10 degrees per second, the pitching is going on over the course of seconds instead of milliseconds. But these converters operate in the kilohertz range, and as such, all these have got to be considered when you're doing the controls to make sure that the systems work together, they don't fight each other, they don't hunt against each other, and all those sorts of things. So with bar control, power factor control, voltage control are all kind of names for not the same thing, but these three affect each other. When you change the bars in and out of the turbine, you're actually affecting its power factor, and you're also affecting voltage changes out where the generator connects to the outside grid. So most often the utilities desire the power plants to operate in a voltage regulation mode instead of a power factor or a bar control mode. And that's to make them analogous or to emulate the same kind of operation a standard conventional synchronous unit would. In the older days, meaning about 10 years ago and beyond, it was okay to draw inductive power. Well, I should say about 15 years and earlier. 10 years and earlier, then if we just did power factor control and didn't draw the bars from the grid to excite these induction generators, then we could operate as close to unity power factor. We wouldn't be moving the voltage around on the grid, and so that was helpful. It was much better than the older units of 15 years ago. But the last 10 years, the utilities really want us to operate the whole power plant as much like a conventional generator. So now we've got to have voltage control and voltage regulation. So it depends on what type of turbine we have here. The turbine, the type 1 and 2s, we find that power factor control with power factor correction capacitors or power factor compensation capacitors. But for a type 3 or 4, we actually operate a capability curve, a active-reactive power capability curve that looks something to the diagram you see there. It's not a D curve like a conventional synchronous machine. You've got the same sort of limitations on the stators and rotor winding heating that presents the ultimate limitations, but you can only get so much apparent power out of the machine as the vector combination of active and reactive power. So that's at the turbine level, but the requirements are always for the wind plant because the wind plant is connecting up to the system. So we may have to put extra mechanically switched capacitors and reactors into the switch yard of the project or power electronics, what I call fax devices here, a static bar compensator or a StatCom to give us complete control of reactive power and active power out to the grid. That will supplement what the turbines may or may not be fully capable of providing to meet the interconnection requirements I alluded to earlier. Okay, next slide. These are just some of the power quality issues here. Power factor regulation that we talked about. Flicker, voltage step change. Flicker is voltage that is moving around a lot. And we'd like that to be absolutely minimal here. Each system can only take a certain acceptable voltage step change, 2, 3, 4%, and generally dictated by what is your voltage change when you switch in and out capacitor bank. We also have to look at harmonics and keep these to a minimum. Generally, wind turbines of old with the type 1 and type 2 produced almost no harmonics. So the more power electronics we put on to condition the output power, the more potential we have for creating harmonics that could be seen onto the grid, and that's not a very good thing, and certainly there's limitations on how much that kind of dirty power can be put onto the grid. Islanding is a condition when there's a fault on the system and your plant are on a line without any other generation on the line, but you still have load. You still have customers or cities on that line that you're feeding into. It's a very complicated issue in and of itself, and usually what we'd like to do is just get offline at that point, let the system restore itself, and then we put the wind power back onto the line after the system comes back up to its normal operations when voltage and frequency is stabilized. Okay, next slide. Just quickly, this just shows the type of protections we put into the wind turbine itself. Again, with that top controller, that multifunction microprocessor, it's got all the protection capabilities, all the protection relay capabilities already built into the wind turbine. So you've got over and under voltage and frequency protection, asymmetrical current, meaning the three phases aren't balanced properly. The temperature on the transformers and the generator needs to be monitored. If we get an overcurrent for either an overload or for a fault, we will need to have circuit breakers prepared for that. We need to synchronize some of the Type 4 unit needs to be synchronized with the grid as such. The induction units are naturally synchronized. The Type 1 and Type 2s and Type 3s are naturally synchronized, so they really don't need much of a synchronization circuit on them. But then also, we got protections as discrete relays also for the main generator that are backup for the controller's protections that are on the left there. So on the right, the main generator circuit breaker is just a standard multi-case circuit breaker to give you instantaneous and time delay overcurrent and ground fault protection. The next slide. This is a picture I took in Hawaii up on the North Point and the Big Island of a wind project we did there. This is actually, you can see, if you look closely, the orange blade, the one orange blade on that the state of Hawaii required us to protect their native nene goose. So that's what we've got to engineer these projects. And these are the kind of things we look at, the connecting circuits of the wind turbines up to the grid, the wind turbine itself, the generator step-up transformer within the wind turbine, a generator, and then a step-up transformer to go from medium voltage to that 35 kV up to the 115 or 138 or 230 kV on the transmission system. We've got junction boxes scattered all around to connect all the components together, switches, and we also got meteorological towers there that will measure the wind conditions on a real-time basis here. So you see a single line diagram of a typical project as such, where all the green wind turbines themselves are feeding in the colored radials into that collection bus in the middle that's blue and reddish. The transformer on the wind turbine can be configured for either a delta connection or a Y connection on the collector's medium voltage collection side here. I know we're getting close to the end here, so I'm trying to speed it up a little bit. But generally on the wind turbine, it's always a solidly grounded Y connection. But on the collection side, it could be a delta or a grounded Y. This really depends on the ground philosophy, the ground protection philosophy of the particular designer. And so you've got to pick one or the other and then accommodate the rest of your ground fault protection based on you pick a delta or a Y connection on those transformers. If you pick a delta, one of the good side is it doesn't allow zero sequence components to flow through the transformer. But on the downside, if you've got a single phase ground fault, you might see as high as 173% overvoltage on the two healthy phases. And as such, if you went with a grounded Y, you wouldn't see those overvoltages, but then you also get, it's much trickier to provide selective coordination between the different protection devices from the grid to the collection bus to the feeder bus all the way out to the wind turbine. Makes it much harder to coordinate all that and get them to not accidentally trip or inadvertently trip in a manner that is not exactly how you want them to. So you pick one or the other and you have to go with it here. But if you're using deltas, then we generally use these grounding transformers here. Next slide. To provide a good return path for the ground fault current, convert positive negative sequence current to zero sequence type currents that would be detected by the ground fault relay. prevent these overvoltages on the unfaulted other phases, help eliminate thorough resonance or the resonance of the transformers when they get in very saturated conditions, creates a nice effectively grounded system, and the grounding transformer can be connected in different configurations also here. The sizing of these transformers are generally about 5% of the current load that you're going to see on that feeder. So if we had, say, 30 MVA is the maximum size we can put on generator collectors because of the ampacity of the conductors we use. And so at 5%, this works out that your grounding transformer should be about 1.5 MVA for if we've got a very large collection feeder. That would be an example of 15 2-megawatt turbines, or maybe 10 3-megawatt wind turbines to give you 30 MVA. Next slide, then. The different feeder arrangements, as you quickly saw on that single line diagram here, really the geography dictates a lot of how the project is going to look, where we're going to put wind turbines, and we do what we call wind siting to optimally place the wind turbines for the wind. And in doing so, this dictates how they're going to get connected by the cabling in between them. So that those feeder circuits go out, they split in these bifurcations. It can be done at the wind turbines themselves, or it can be done at junction boxes. It could be done at switchgear also. Different companies do it different ways. But you can have a simple radial layout of the turbines on a one line going out, or you can have it split into those bifurcations, into those splits, or you can actually have a loop out there, which is advantageous for redundancy. But you've got to put breakers on each end of that loop of those wind turbines there. So when you do get a fault and that loop opens up, those breakers have to be sized for the full current they're going to see on that side of the fault. Some of the other considerations for these collection feeder cables, the number of feeders you can get on the cable is really dictated by the ampacity of the conductors you're using. We generally use aluminum type of underground cable in either standard underground rural distribution type of cable constructions, or in Canada they use this tech cable. But these are generally just your normal underground insulated type of cables here. The cables have to be protected from normal operating currents, inrush currents, and fault currents, obviously here. And the Schweitzer 351 is the most commonly used breaker for those feeder breakers. But the other thing you got to consider on the feeder is voltage rise and drop. I mean, the cables, underground cables, will tend to be capacitive, which will tend to drive the voltages up. Overhead constructions tend to be inductive, which tends to have voltage drop as the cables get longer and longer. But you've got to do this voltage rise calculation to figure out what your voltages are going to be from the wind turbines back to where you're collecting it and connecting them up to the grid. And you've also got to calculate the losses within the grid, the installation costs, and things like that. And of course, we use, again, standard connectors, again, from the distribution industry here at 200 and 600 amp. It's kind of what they look like in the switchgear at the bottom of the wind turbine for a one that has a transformer up on top. The top row of black ones are from the wind turbine itself. They go through basically a big SF6 breaker, and then it goes output on those two rows on the bottom that are piggybacked together. And that's a very conventional way we do that in the United States. Next slide. Underground versus overhead construction, all the things you need to think about when you do that. And aesthetics is certainly not the least to be considered if you look at the two pictures here. So on the left is highly preferred over the right, and actually if something were to break off or ice were to develop on those blades, you wouldn't want them throwing that ice and onto those overhead conductors that you see in the picture on the right. Next slide. All the different studies you got to do for the electrical analysis and of the collection system as such, and then all the drawings you need to generate. So I won't go through all those. We're getting only a few minutes to go here. And then for underground constructions, that we're using either XLPE or EPR, crosslink polyethylene insulated underground cable, or the rubber type of insulated cable here. This is just an analysis of the two and a comparison of the two. And in general, crosslink polyester or tree-resistant crosslink polyester is what is generally used in the industry most often. And some of the other things that need to be considered when you're doing this. So here's the underground cable, and with a diagram that shows its major components. And here's the overhead and different types of cable used in overhead. The design of well, you should get to the slide that says design of wind power plant substation. And this just shows the components that are in a standard substation. Everything collects on the left to the collection feeders, and then kind of moves to the right, and then you've got the tower, the deadhead tower, that actually sends the power out to the transmission system. For lack of time, I can't go into great detail about that, but we use just standard industry substation designs. Nothing really unique about that for the wind industry. So we've got transformers, breakers, and disconnect switches, and voltage transformers and current transformers for setting and everything. And on top, you'll see the capacitor bank in the substation being used on this project. Next slide. Within the power plant controllers and then the SCADA system. So this is, the wind turbines themselves give you a degree of control functionality, but the utilities really want us to operate as a conventional plant, and so these power plant controllers and SCADA allows us to do that. As you can see, it's monitoring the wind turbines, the MET station, breakers, giving any cautions and alarms, and it's feeding the signal in and out to various vested, interested parties who want to see what's going on in this power project. So the power plant controller really allows the part to be run as desired, to give you system reliability concerns, economics, to make sure it's operating as efficiently as possible, operations of putting it together, the project together, and the operational economics as such. Next slide shows the power plant server, which is a PLC-based converter that actually works with the SCADA computer server, but its only function is to give power plant control and not a lot of reporting in and out or interconnection with the outside world here. But it affects the frequency and the voltage control and other control functions you want the power plant to perform. So next slide, a little bit more of the type of functions and controls of the power plant controller. And this is, next slide shows a diagram of the three major active power controls. So we've got the absolute control in the upper left, where we can stave off peaks of the wind, and if the load is less than what the wind can provide at any given time, we can actually curtail the plant and give the desired amount of power for exactly what the load needs. Sometimes we need to ramp that power over time, which is the upper right diagram. And then we've got this delta power control. We can reserve a little bit of power, hold it back, so that we can do things like under frequency regulation. For frequency regulation, it's easy when you have too much. When the frequency is high, it means you have too much generation, and we just spill wind and lower our generation. But if we're operating at the full power the wind can provide, we can't get more power out of the wind than it can provide. So if we step it back 5 or 10%, like the orange line shows, then we've got some headroom to actually move up and send more power into the grid and kind of affect the type of control you see in the lower right there. If you look at that diagram after this, after the presentation, you'll see the over and under frequency responses here. We can do different types of scheduling and ramping controls with these controllers. And we've got to meet the voltage and frequency criteria. And they're basically come from the North American Electric Reliability Council, who writes the standards for how the transmission operates. We've got to run in between those colored lines for frequency on the left and voltage on the right. And you'll see we've got to operate what we call low voltage ride through all the way. If a fault gives us zero voltage on the system until the fault clears and the system restores and brings voltage back to our project, we have to be able to not disconnect the turbine and keep them running so when voltage does recover in a few seconds, we can actually kick off and aid the system in recovery. There's a new concept since 2005. Before that, we just get offline and wait for 10 minutes. And this slide, the next slide is the PQ control on the project level. I talked about it on the turbine level, but on the project level, what you'll see here is the wind turbine and then the compensation equipment and where we might put the compensation equipment. On the bottom of the left, it says no compensation equipment. And now going to the right, we see where we can provide compensation just with switch capacitors. Next to the right, we can do the compensation with just STATCOMs. And on the far lower right, we can see a combination of STATCOMs and switch capacitors gives us the most cost-effective means for a wind power plant control solution for voltage control. And with that, I'm only a few minutes late. So I appreciate your attendance and your interest in the class.